Hello, folks. This video covers 6.4 from your textbook on amplitude and period. So it's not a surprise. Now that you know how to graph the basics of a sine and cosine function, we can do all kinds of stuff with those functions. So take it back to all of your other types of parent functions, particularly a quadratic that we do a lot of stuff with. We translate it, right? Up, down, left, right. We can stretch it every which way. We can flip it over, we can make it, we take that parent function, then we can do lots of things to it. Well, things are no different with sine and cosine. We can take that original wave that has its particular qualities and change the equation of it to affect the graph. Particularly, this section covers amplitude and period. Now, the word amplitude is probably exactly what you think it is in terms of, how we use it in everyday language. What I need you to understand about amplitude, and I'm going to be very informal here, is that it's just, oh, my clothes are ready. It is how high does the function stretch? Very informal, but that's the deal. How high does your function stretch? That's what amplitude is. Okay, so I want you to consider just a regular function y equals capital A times the sine of theta. By definition, we say that the amplitude of that function is equal to the absolute value of A. So that's a big takeaway in this first part. Amplitude is equal to the absolute value of A. For instance, if I take just our regular parent function that you already know how to graph very well, y is equal to the sine of theta. And let's just go ahead and graph that very quickly. So hopefully you're getting better at this by now. We know the y values are going to stretch from -1 to 1. We know that it's going to start off at 0. And, we just are doing a basic sketch here. It's going to go up, back down to 0, down to -1, and back up here, and then it's going to continue. The idea here is that the amplitude, I have no variable here, or technically there's a 1, we just don't need to write it, which means that the amplitude, which I'll just call A and P, is the absolute value of 1, which is equal to 1. And by looking at the picture, the amplitude is this distance here, the distance that it stretches, not fully, not from -1 all the way to 1, but from that x-axis upward or the x-axis downward. Okay? We can also get some space here. Let's do another example. If I were to take the function y is equal to negative sine of theta. So just like you might guess, and we haven't done one like this quite yet, but like you may guess, the x and y coordinates are still the same. The only difference, if we have that negative out front, is that it's going to reflect our function. So instead of starting at 0 and going upward to 1, everything is opposite. It's actually going to go down, then back to 0, then up 1, then back to 0. So the negative sine function looks like this. Okay, variable in front of sine is -1. So then my amplitude is going to equal the absolute value of -1, which is still +1. So again, it's that distance away that the function maxes out from the x-axis. Okay, so you may see some examples. Let's call this example 1. Okay, and let's just say I want you to graph, I guess I just could have written this, huh? Okay, we're going to graph the two functions on the same graph. I want you to graph y equals the parent function cosine of theta and y equals 4 times the cosine of theta on the same graph. So let's start with the parent function. Again, hopefully you're getting pretty good at this. to where if I graph, I know it's going to come down to, well, actually, we have to be particular here. Let me graph a new one by hand. So as you can see, I'm going to anticipate this 4 means that this guy is going to have an amplitude of 4, which means from the x-axis it's going to stretch upward 4 and downward 4. So I actually need a bigger y-axis than what we've been used to graphing these functions. Okay, so when I graph cosine, let's just do one very small here. 2, 3, 4, 2, 3, 4. So I'm at -1, +1. And then let's go ahead and label this one since this is a full example. Remember, we care about the 4 corners on our unit circle. The first one being pi over 2, the second one being pi, the third one at 270 degrees is 3 pi over 2, then we're at 2 pi. Okay, so cosine of theta, let's do that one in blue. That one starts at +1. And then at the 4 corners, it goes down 1, down to -1, back up to 0, back up to 1. And then it continues forever and ever amen because it is called a periodic function. And we can even put an arrow on this side. Okay, so that is y is equal to the cosine of theta. The only thing that this amplitude change will do, so if this amplitude is 4, is that those max and min values now will peak out at 4 and -4. So instead of y equals 4 times the cosine of theta starting out at 1, it's going to start way up here at 4. Okay, then it's going to hit 0, just like this one does. Then instead of a min of -1, it's going to have a min of -4, back up to 0, back up to +4. And if we had the time, we could make a table of values just to show you that, you know, putting a 4 there doesn't change these middle terms here that are back at 0. But again, for the sake of time, that's the basics of it, is that amplitude changes your max and your min values of your basic trig functions. Okay, so there's our amplitude. The next thing to discuss is period. Now, recap, we know that the period of sine and cosine is 2 pi. And that's how long it takes for it to get through one cycle. So let's write that. So recall the period of sine and cosine is 2 pi. Period of sine and cosine is 2 pi. Therefore, we can say the following. If y equals the sine of k theta and y equals the cosine of k theta, where k is an element of the set of positive integers. Positive integers. So just saying it has to be a positive number. So we have the only difference between this and our regular parent function is this variable here, k, that's going to be in front of theta. If we have these two functions, then the period of each function, well, let's just say the period equals and I'm going to do this in a different color because it's the most important. Period equals 2 pi over k, where k is greater than 0. 2 pi over k. So this is the second big takeaway from this video. Amplitude was all about the absolute value of a. Period is 2 pi over k, and you just have to solve for what k is, and then that variable k goes in front of theta in the original function. Okay, so before we look at graphs, and what the graph does to the period, I just want to do some basic examples of finding the period from a given function. So let's do example 2. And all I want to do for these is determine the period. And we'll do a couple of examples. So determine the period. Example A, if y is equal to 1/2 times the sine of 4 theta. If I want the period of this, again, you're going to go up to that function there that I have bubbled up in blue, which is saying that in the function given to us, my number in front of theta is 4, which if you're looking at these functions, that's what k is. So if k is equal to 4, then that implies that 2 pi over, instead of k, 2 pi over 4 is the period, which if I just reduce that is going to be pi over 2. So the period of this function is pi over 2. So let's think about what that means. This means that's how long it takes the sine function to get through one cycle. So if we were to actually graph this, which we'll get to in a second, that means it takes that, specifically, let me think to say this right, 1/4 of the amount of time to get through one cycle compared to the parent sine function. Let's do another example, B. Again, I want you to determine the period of the function y equals 5/8 times the cosine of theta over 10. 5/8 times the cosine of theta over 10. So the first thing to do is identify what is k. Well, k is the number in front of theta. Well, technically, theta over 10 is the same thing as 1/10 times theta. Therefore, we can say k is equal to 1/10. That implies that 2 pi over 1/10 is the period. So I just need to simplify this guy. Well, remember, when you divide fractions like this, dividing by a fraction is the same thing as multiplying by the reciprocal. So let me write it that way. That'll be 2 pi times, instead of 1/10, times 10 over 1. And if it helps you to put 2 pi over 1, do that too. And then we multiply straight across. 2 pi times 10 is 20 pi. And typically, when you're talking about period, if there's pi involved, you leave your answer in terms of pi. So that's just how to determine the period. Now we're going to do an example where after you find the period, we're actually going to graph it and see how that affects the picture. So determine period, then graph. Determine period, then graph. Okay, given the function y equals the cosine of theta over 2. Y equals the cosine of theta over 2. So we're going to determine the period first, just like we did with these examples above. So the first thing to do is determine what k is. So remember that theta over 2 can be rewritten as 1/2 theta, which means k is equal to 1/2. So if k is equal to 1/2, then that implies that my period is 2 pi over 1/2, which again, dividing by a fraction is the same thing as multiplying by the reciprocal. So that'll be 2 pi times the reciprocal of 1/2 is 2 over 1. We multiply straight across, and we've got 4 pi. So the period of this function is 4 pi. So let's think about what that means. The regular cosine function has a period of 2 pi. If this one has a period of 4 pi, then that means it takes twice as long for it to get through a cycle. Twice as long for it to get through a cycle. So let's graph that and see what that looks like. So I already know if I'm going to go ahead and label my axis, I'm going to stretch this, that I'm going to have to go beyond 2 pi. Now, my amplitude has not changed, right? There's no number in front of the cosine. Therefore, I know my amplitude is still 1. So on my y-axis, I know my mins are going to be -1. My max will be +1. If it's going to take me longer than 2 pi, particularly it's going to take me 2 usual cycles to get through that period. So let's say that this here is 2 pi, and that the full length is 4 pi. So half of that's going to be pi, half of this is going to be 3 pi. And, you know, you can put your other values in the middle there. The other thing to think about, and you could do this in a few different ways. You can use the calculator to aid you, or you can just use what you know about the unit circle and plugging it in instead of, you know, theta, the cosine of these numbers, it's the cosine of these numbers over 2, right? So technically, as we graph this, so if I'm plugging in pi, technically this is going to be the cosine of theta over 2. I'm sorry, pi over 2 when I plug that in. Well, and you and I know that the cosine of pi over 2, well, hold on. Let's go back to 0. At 0, I know it is 1. Cosine, the x value at pi over 2 is 0. So I know that that's what this is. Now, remember, pi over 2 is technically right here. But what this is when I substitute pi into this function, right? That's where I get pi over 2. Same thing, when I substitute 2 pi, then I get the cosine of 2 pi over 2, which is the cosine of pi, which is at -1. Then if I substitute 3 pi, then I get the cosine of 3 pi over 2, which is back to 0. And then if I substitute in 4 pi, I get the cosine of 4 pi over 2, which is technically the cosine of 2 pi, which is 1. So again, you can use the calculator to aid you in getting those coordinates, or just using what you know about plugging these values in and what you know about the first rotation of the unit circle. Okay, so that's how you find the period and then graph it. Again, as we said before, the typical period would end here, 1 to 2 pi, or 1 to 2 pi, but now it takes an entire 4 pi for it to get through its entire cosine function. Okay, the last type of problem that you're going to encounter is coming up with equations. So number 4, you may be asked to write an equation. Write an equation of the sine function. Write an equation of the sine function with amplitude of 6.7 and a period of 3 pi. Amplitude of 6.7 and a period of 3 pi. So it's given us the information and wants to know what the equation is given this. So the equation has a template, I'll say, or a general form of y is equal to a times the sine of k theta. If we put together what we just learned about amplitude and period, this is what that equation would look like. Okay, so 2 things to note. With amplitude, since we know a is technically the absolute value to get that, then that implies that we could have a plus or minus 6.7 in front of sine. Okay, using what we just learned about period, k is under 2 pi. So the period is equal to 2 pi over k, I'll say. Okay, so using this formula, then our period, it says, is 3 pi. So now I'm going to substitute 3 pi equals 2 pi over k. So if we can solve for k, then we can plug that in and we're done. So to solve here, you can do a few different things. If I put the left side over 1 and cross multiply, then I end up with 3 pi k equals 1 times 2 pi, which is 2 pi. Then if I divide both sides by 3 pi, then I get k equals 2 pi over 3 pi, and then pi over pi is 1, which implies that k is just equal to 2/3. So I already have my amplitude over here. I now have my k based on what we know about the period. So then we can say that our final answer would be y equals, and then you can say plus or minus 6.7 rather than writing two different functions. Plus or minus 6.7 times the sine of 2/3 theta. And then if we graph that, we would see it having a stretched amplitude, and the period of 3 pi means it would be, again, stretched horizontally as well, taking a longer time to get through one cycle. So that's the basics on how amplitude and period have effects on the parent functions for sine and cosine.